So autonomous differential equation is an equation of this kind. So derivative of the function that we are looking for is supposed to satisfy this condition that is given by this function g and is a function of y. The independent variable doesn't appear explicitly on the right-hand side of this equation. So example of an autonomous differential equation, very simple, y prime equals y. Or this is autonomous, or y prime equals 1 plus 2y squared. I'm using y prime. We could also use dy over dt. This notation is shorter, but means the same. It means derivative. And for example, another example, y prime equals, let's say, x over y. So that would be x times 1 over y. This equation is not autonomous because the right-hand side is a function of x as well as a function of y. But this equation is a separable differential equation. So basically we have the class of separable differential equations. Equation is separable when you can write this equation that way. Y prime equals, let's say, some function f of x times some other function g of y. This is a separable differential equation. When the function f is equal to 1, then you get this equation y prime equals g of y. And this is an autonomous differential equation. So autonomous differential equation is a subclass of separable differential equations. Okay, so let's say that we have a given autonomous differential equation, i.e. we have an equation of this kind. Autonomous differential equation. The right-hand side doesn't depend explicitly on the independent variable, which is t in this example. And then let's define one class of solutions which are on one hand side very, very, very simple. And by definition, an equilibrium solution of this differential equation is any constant function that at the same time is a solution to this differential equation. Okay, so let's think of this that way. So we have the y-axis. We have the t-axis, sometimes called this x-axis or sometimes called this t-axis. Think of this t as time, or sometimes we can think of this as x-axis, the same thing. And then this is the y-axis. And let's say that this is the given differential equation. Solutions to differential equations are functions. So let's say that one function looks like this, maybe looks like this, and this is, let's say, y1 of t. And let's say that this function is a solution to this differential equation. Is this function an equilibrium solution? No, because it doesn't look like a constant function. Let's say maybe here's another function. Maybe another function looks like this, and something like that. And this is y2 of t. Let's say that this function is a solution to this differential equation. But again, this function is not an equilibrium solution because it doesn't look like a constant function. But now let's take a function that looks like this. Let's say this is maybe 7. And consider this constant function 7. So the constant function 7 looks like this. It's a straight line. So this is the function y, well, let's say y of t. This is the constant function that is equal to 7 all the time, 7. And let's say that this is a solution to this differential equation. Then this solution would be classified as an equilibrium solution because it's a constant function. So equilibrium solution to a differential equation is just a constant solution. Let's say, for example, here's another function. Doesn't look like a constant function, but if this is a solution to this differential equation, it's not equilibrium because it's not a constant function. So equilibrium solution is a constant solution to differential equation, constant solution. Okay, so given an autonomous differential equation, how do we find all equilibrium solutions. Notice one thing, even if you take this constant function 7, if you compute derivative of this function, constant function 7, derivative of this function is going to be 0. So we'll look at the right-hand side of this equation, and we'll set the right-hand side of this equation, g of y equals 0. And then all functions that satisfies this equation, those are exactly the equilibrium solutions, i.e. the constant solutions to this differential equation. Okay, let me give you one example. Just admit this person. Perfect. Someone is saying that 0 is derivative of this constant function. Exactly right, because we know that derivative of any constant function is 0. So essentially, if I have an autonomous differential equation, equilibrium solutions looks like this. They're constant solutions. Maybe there's few of them, maybe only one, maybe there's no, but the constant solutions, those are the equilibrium solutions of a given autonomous differential equation. Okay, let me give you an example. Okay, and then what we'll be doing is we would like to classify equilibrium. We would like to classify equilibrium solutions, and basically we will be considering three types of equilibrium solutions. So let's say, for example, we have a given autonomous differential equation. So dy dt, and that's equal to, we use this function g. Okay, so let's say this is equal to g of y. So let's say we have given autonomous differential equation. And let's say that we are given a few solutions. Let's say that we are told that this function is a solution to this differential equation. Is this an equilibrium solution? No, because the function doesn't look like a constant. Let's say that we are given that also this function is a solution to this differential equation. This is also not equilibrium solution, but let's say that we know that this constant function, let's say this is some number, I don't know, k. Okay, and consider this constant function y of t equals k. And if this is a solution to this differential equation, then this would be an equilibrium solution because it's a constant function and it's a solution to this differential equation. On the other hand, let's suppose that we have maybe different differential equation, maybe dy dt equals maybe some function h of y. And let's say that we're given a few solutions. Maybe this is one solution to this differential equation. Here's another one, here's another one, another one. And let's say on this level k, we have another solution, which is a constant, y of t equals a constant function, a constant solution. Then this is also an equilibrium solution. Equilibrium solution, this is another equilibrium solution to this differential equation. And notice one difference. Just unmute this person. Notice one difference. Here, if you take another solution, another initial condition, maybe this is 17, and maybe at 0, this is a solution that's 17. When you look at the limit of this function, call this function f. When you look at the limit of this function, when t goes to infinity, f of t, notice one thing, this function will be asymptotically approaching the equilibrium solution. So if you start with, not necessarily at this point k, but if you start a little bit above or maybe a little bit below the equilibrium solution, maybe this is another function s, and then you compute the limit of this function s of t. When t goes to infinity, then you also get the number k. You will see that the other solutions will be asymptotically approaching the given constant solution, And if this is the case, then this equilibrium solution will be classified as stable. Then this equilibrium solution will be classified as a stable Sometimes it's called locally stable or sometimes it's stable. The same thing, I'll probably say stable because it's short. But this would be classified as a stable equilibrium solutions. On the other hand, we have the opposite situation here on the right-hand side. Exactly. Okay, on the other hand, we have the opposite situation, so to say. If this is an equilibrium solution, the constant function that is a solution to this differential equation, then notice one thing. When you take different initial condition, maybe this is 7, and look at this function, call this function f, for example. If you compute the limit of this function, you won't get the number k. The function will be going away from this equilibrium solution. And it will be doing it will happen exactly the same when you start with the initial condition that's a little bit below the constant k. If you take this function, the function will never be approaching this equilibrium solution. So in a way, this is the opposite situation. And when we have this case, then this equilibrium solution will be classified as not stable, or sometimes we'll just say unstable. And there's one more case that could happen, namely something like this. So let's say, again, we have some differential equation given. So dy, and let's say it's autonomous, dy over dt, and it's equal to some expression of y, but it doesn't involve t explicitly. So it's an autonomous differential equation. And let's say that we're given this is one solution of this differential equation, this is another one, and here is one solution on this level, maybe 20, if I can see correctly, but this is 20. Okay, and this is 20 is the constant function. So y of t equals 20. You know, it's a constant function. So notice one thing. It's a constant function, but then when you want to test this function for stability, whether or not the solution is stable or not stable, and then you will see that there's one thing. The nice thing is that when you look at the edit point that is less than 20, let's say, for example, you take 19, and you take the function that starts at 19, you will see following the direction line, you will see, call this function f, for example, you will see that the limit when t goes to infinity, f of t is equal to 20. Okay, but then what's happening is, so this is, and also if you, maybe this is 19 and maybe that was 14. Take another function, maybe this is function g. You will see that the limit is also equal to 20. And that's fine, but because if you take any number, like for example 21, and look at this function, what's happening, the function really goes away from this equilibrium solution very, very fast. If you take 20.5, even very close to, like at this point, this solution will go away from the equilibrium solution. So sometimes we'll say that this is semi-stable, because on one hand side, this looks like it's like half stable, so to say, because the good portion is this one. It looks like stability, but then if you take any function that starts above the point 20, we don't have this condition for stability, so it's half stable or semi-stable. So this is what could happen if you have an equilibrium solution. Looks like this. This equilibrium solution is semi-stable because this is the good portion, the function that starts above this point k. They will be asymptotically approaching this constant function, but the function that's a little bit started at a point a little bit less than k will not. And here's exactly the same, but the opposite. So if you take any point that's a little bit bigger than k and take any function that starts at this point, the function will be going away from the equilibrium solution. So this one will be semi-stable. Both of those solutions would be semi-stable. So let's do now an explicit computation. And let's find, so I'm going to have a autonomous differential equation, and I want to actually compute all the equilibrium solutions. So I take this simple differential equation, y prime equals y prime equals y. Another way how to write this differential equation, we could say derivative of this function y, derivative of this function y with respect to t, let's say, with respect to t is equal to y. Okay, so this is a very simple separable differential equation, which at the same time is autonomous. It's separable, but it's autonomous differential equation. So let me solve this. Because it's separable, first of all, let me show you how to solve this just the usual way. So let's solve this separable differential equation as we usually do. So let's multiply both sides of this equation, and multiply, what I mean multiply is I mean multiply formally, because dy over dt is a symbol rather than a number. But we can think of this as formal multiplication. So when I multiply both sides by dt, then on the left-hand side, I get dy, and this is going to be equal y times dt. And then I want to separate the x's and y's, or the x's and t's. So I'm going to divide both sides of this equation by y. That will give me dy divided by y equals dt. And what I'll be doing now is I'll be integrating the left-hand side and the right-hand side of this equation, this side with respect to y, and this with respect to t. Okay, so integral dy over y is ln of absolute value of y, ln of absolute value of y, and plus some constant c. But I'll take care of this constant c just in 1 second when we'll be doing the other integration. And on the right-hand side, we get integral of dt, well, just t, and then plus some other constant c. And now this constant c is also for the first integral. And let's do the same trick that we did the other time. Let's take the exponential function, let's apply the exponential function to the left-hand side and to the right-hand side of this equation. So we get e to the ln of absolute value of y, that's equal to e to the t plus c, e to the t plus c. But now we mentioned this formula the other day. This is exactly the same as e to the t and then times e to the c. So absolute value y, and that's equal to, this is e to the c, well, okay, e to the c times e to the t. Okay, and notice one thing, everything made perfect sense, because look, the right-hand side, this is the exponential function e to the t. This is the t-axis, and the function e to the t looks like this. This is the function e to the t. So this is a positive number. And notice one thing, e to the c, no matter what the c was, then e to the c is also a positive number. And the left-hand side is absolute value, so it's a positive thing. So the left-hand side is positive, and so is the right-hand side. Make perfect sense. But now when I want to solve this equation for y, this is an absolute value of y. I want to know what y is, what the solution itself is. So when I skip the absolute value function, I can allow this number to be negative as well. So when I skip the absolute value function, I get y of, I can say y of t, and that's equal to, I'll use the same letter c, even though it might be different letter. I'll indicate that in 1 second. I'll say c times e to the t. And then I'll have to specify what c is. Well, where I can say where c is just completely any number, any constant, any number. And this is the general solution of this differential equation. And notice that also, okay, so notice if you take this constant, take this constant c to be 0, then what function we are going to get? Y of t equals constant function 0. Because if c is 0, then this is 0. And constant function 0 is also a solution to this differential equation. So, okay, so question is now for you. All solutions of this differential equation look like this. Okay, so this is, again, this is the y-axis, this is the t-axis, and then we sketch a few solutions. All solutions look like this, c times the exponential function. So take c equals 1. When c is equal to 1, this is just the exponential function. So that's the function e to dt. This function is a solution to this differential equation. Take this constant c to be maybe 2. So how does the function when c is 2? So this is 1. And then we have the level 2 here. And when c is 2, this is another function that looks like this. And that's the function 2 times the exponential function e to dt. This is also a solution to this differential equation. Take this constant c to be 3. And you know, okay, let me just sketch the last one, 3. Then e to the 3 times t, this is how the function looks like. So this is 3 times exponential function. And take negative 2. So this is negative 1, negative 2. Okay, so this is the function negative 2 times exponential function. So the collection, the family of all those functions, this is negative 1 times exponential and so on and so forth. All the functions looks like this, but there is one function, namely this one. The constant function, this is the constant function y of t equals 0. This is the constant function. This function is a solution to this differential equation. And those are all solutions to this differential equation. So now the question is for you, which of those functions is an equilibrium solution?
Y of t equals 0.
Perfect, this is excellent. Only one function is equilibrium solution, and namely that's this one. Excellent. This is the constant function 0, this function. And see, this is an autonomous differential equation. If you shift this function to the left, to the right, it's still solution. But if you shift the 0 function, doesn't change this anything. So we have the equilibrium solution. And if, okay, so also question for you, how would you classify this equilibrium solution? This is not stable, or in other words, unstable. Okay, so the equation was this one, y prime equals y. Excuse me, what I did was I wanted to solve this because it's separable. So I said dy over dt, derivative of this function y with respect to t is equal to y. And then what I did, we multiplied formally both sides of this equation by dt. Then we get that dy equals y dt. And then what we did, we divide by both sides of this equation by y, and that will give me dy over dt equals dt. And then when I integrate the left-hand side and the right-hand side, I get ln of y equals t plus c. So the general solution of this differential equation is a collection of all functions that are given by this formula, where c is completely any real number. So by this, I mean the collection of all real numbers, and this statement here means that where c is any number, positive, negative, or 0. So when c is equal to 0, that will give me the constant function 0. This function is a solution to this differential equation. When c is equal to 1, let's see, this is 1. When c is equal to 1, this is a solution e to the t. Where c is equal to 2, well, c is equal to 2, I have the solution 2 times e to the t. Where c is equal to negative 2, I have so many solutions. Okay, I don't want to draw more of them, but we have a lot of them. And there's only one solution that is the constant function 0. And this solution, first of all, first of all, this is an equilibrium solution because it's a constant function and it's a solution to this differential equation. And because of the behavior of the nearby solutions, we can classify this one as unstable equilibrium solution to this differential equation. We'll sketch this. Sometimes they call this a phase plot or the phase portrait. So basically what is this is we are going to take the right hand side. Remember the equation was dy over dt. That's equal to, well, y. That's equal to y. But in general, this is the right hand side of this differential equation. So some function g of y. See, every autonomous differential equation looks like this. dy over dt is some function of y on the right hand side. So in this example we are looking at now, the equation looks like this: dy over dt equals y. And the function g of y is very simple function y. So what we can do, we can, for a moment, let's don't think of this y as a function of t. Let's just think of this as in calculus 1, like the function, like the diagonal line g of x, f of x equals x. Let's think of this that way for a second. Okay, so let's sketch this graph of this function g. This is my g-axis, this is my y-axis. I'm not even thinking that the y really is a function. For a second, I'm thinking of this as in calculus 1, very simple. So it's y, and this is g of y. Okay, so how does this function f of x equals x or g of y equals y looks like? Very simple, because it's just a diagonal line. That's how this function looks like. That's how this function looks like. And then one fact that we'll be using is also from Math to A. We know, see, what is g of y really? What is g of y really? What is g of y really? G of y really is the derivative of a solution of the function y. So g of y is the derivative, but we know when derivative of the function, when derivative of the function is positive, here, from starting from 0, excellent, the function will be increasing. So, okay, so let's see. So how we can think of this, even if we don't have the direction field. So this is differential equation, and I want to understand what does this equation says and how does the solution look like. So I'm looking at all functions of t. So this is the t-axis. Well, if the differential equation is this one, then first of all, I look at this equation g of y equals 0, or in other words, y equals 0. That will give me this point. This point is the equilibrium solution, namely the function, the constant function y equals 0. This constant function y equals 0 is the equilibrium solution. Okay, but now if you take any point that's a little bit bigger than 0, for example 1, and how does the solution that starts at this point looks like? The derivative is positive, so the function will be increasing. So we'll indicate this by putting this little arrow here, and this arrow will correspond to a solution that looks like this. So this arrow does a it's like a convention indicating this solution to this differential equation. If you take any point a little bit bigger, maybe 2, so we look at this point 2, and the solution also has to be increasing because we don't know the solution, but we know that the derivative of this solution is positive. So the solution has to be increasing, and we'll indicate this putting this little arrow in the increasing direction, and so on and so forth. So this arrow will correspond to this solution and so forth. Okay, let's see what's happening for points less than 0. So for example, when I take this point -1, here's -1, and I would like to know how this solution looks like. I don't know what the solution is, but I do know that the solution derivative of it is negative. Okay, but when the derivative is negative, the function is decreasing. The function will be decreasing. The function will be decreasing, so something like this, and we'll indicate this by putting this arrow. So this arrow really means that the solution looks like this. We don't know exactly how this solution looks like because we don't have the formula, but we do know that this solution has to be a decreasing one because its derivative is negative. And we can take any one like this that would correspond to the solution like this. Okay, so because we have this situation, then 0 is an equilibrium solution to this differential equation and is unstable. And it's unstable. So let me show you exactly what we did, but in a little bit nicer picture. So this one. So again, the differential equation was this. And step 1 was find equilibrium. So we took the right-hand side of this equation and we set the right-hand side to be 0 and nothing to do because 0 is the equilibrium solution. Okay, and then we draw this we draw this function g of y equals y. So that's the function g of y equals y. At this point, exactly at this yellow point, the function is 0. So this point, this yellow point right here, corresponds to this constant solution 0. This is an the equilibrium solution. But then because the derivative here is positive, then we have something like this, and derivative is negative, then we have like that. So because of that, it's unstable. Okay, very simple example. I want to do very quickly one more example, but the same. So now the differential equation is not as simple as in the previous example. The differential equation is this. So another way how to write this differential equation is to say dy over dt is equal to, okay, let me just add this person. Dy over dt, it's just a different way how to write this differential equation. Dy over dt equals 2y minus 3y squared. Okay, so that's my differential equation. And question for you, well, obviously it's separable, but question for you, is this differential equation an autonomous differential equation? Yes, it's going to be autonomous because the right-hand side doesn't depend explicitly on time. So we can solve it's separable. We could solve this even though it would be, we get a formula that would, okay. So let's try to find, first of all, let's try to find all equilibrium solutions. And then we're going to classify them. First of all, how do we find all equilibrium solutions? I'm going to look at the right-hand side of this equation, which is 2y minus 3y squared, and I'm going to set the right-hand side of this equation to 0. So maybe we can factor y, the function y, so I get y times, and this is 2 minus 3 times y. Okay, and this is equal to 0. So one equilibrium solution we will get is the function y of t equals 0. This is y, one equilibrium solution to this differential equation. And the other one is 2 minus 3y. 2 minus 3y equals 0. So 2 is equal to 3y. So if we divide both sides of this equation by 3, I get 2 over 3 is equal to 1. Okay, so I have another equilibrium solution. Two functions. So okay, this is the y-axis, this is the t-axis, and maybe this is Okay, so one equilibrium solution is the constant function 2 over 3. So this is 2 over 3. And the constant function looks like this. So that's a constant function y of t equals 2 over 3. And what is the other equilibrium solution? The other equilibrium solution is the constant function 0. So here's 0. And here's the constant function, which is the same as the t-axis, really. But this is the other function, y of t. Two functions, y of t equals 0. This is one equilibrium solution, and another one is 2 over 3. But now let's try to classify those equilibrium solutions. See, okay, so what we do is we can sketch the graph of the right-hand side of this differential equation. So I'm going to define this as this function g of y. And I'm going to see, I want to see how the graph of this function looks like. So here's my g of y-axis, here is my y-axis, excuse me, y-axis. So one, it really is a polynomial of degree 2, 2y minus 3y squared. This polynomial is equal to 0 at 0, so this is one root of this polynomial, and another root of this polynomial is the number 2 over 3, which is approximately, I don't really know, but 0.5 or 6, something like that. 0, okay, it doesn't matter, 2 over 3, this is a number. 2 over 3. Well, okay, but how does this polynomial look like? This is a negative at y squared, so the polynomial is going to look like this. So the polynomial is going to look like this. Okay, so this is exactly the function g of y equals 2y minus 3y squared. Okay, so now let's see. Okay, now let's see. Let's try to classify maybe this equilibrium solution 2 over 3. What's happening here? The derivative is positive. The derivative here is positive, positive, positive. So when I stay between 0 and 2 over 3, derivative is positive. Let me think for a second. When the derivative is positive, then the function is increasing. Okay, so the function is increasing, so we'll get something like that. We'll get something like that. And when the derivative is negative, then the function is decreasing. So this is the decreasing direction. So now what does this mean? How does the other solution, okay, let's also classify 0. Let me see. When the derivative is negative, the function is decreasing. Okay, so the function is decreasing. So this is the decreasing direction. Okay, so here was the differential equation. And we could solve this using separable variables, but the formula would be complicated. But let's try to understand what does this equation, how does the solution looks like? Two solutions we already have. One is the constant function, this one, 2 over 3. This is a solution of this differential equation. And this constant function 2 over 3 corresponds to this point. This is the equilibrium. Another equilibrium is the constant function y equals 0. And this corresponds to this little point, 0. But now, what's happening? 2 over 3. Okay, question for you. Is 2 over 3 stable or unstable?
Stable.
Perfect. This constant function is a stable solution. Solutions of differential equation, at least when the function, the right-hand side is continuous and so is the partial derivative with respect to the independent variable is continuous as well, then the solutions never cross. In particular, in this example, the solution cannot cross this one, but it has to be increasing all the time. So how does the solution has to look like? It has to actually approaching asymptotically the other solution because it has to be increasing and it cannot cross. So it has to look like this. If you take another solution, well, it'll have to look like this. And if you take another solution that starts at this point, because this solution is stable, the function has to look like this, and the other one has to look like that. And what's happening on when your initial condition is -1, for example? Well, when it's -1, the function will be derivative is negative, so the function is decreasing, so the solution will look like this. And another solution will look like that. So that will give you idea how this solution set to this differential equation looks like, even without solving anything. So you have this differential equation. It's an autonomous differential equation. So we understand how the solution looks like because we can sketch the equilibrium solutions. Here's 1, 2/3, the constant function. Here's another one. And then we classify stability of those two equilibrium solutions. This one is stable, or sometimes people call it locally stable, same thing. This one is stable. And so the other solutions will be approaching this stable solution, but the other one is not stable, it's unstable. So the opposite situation will happen. If you take any solution that starts at -1, it will not be approaching this one. The opposite will happen. It'll be going away, and so will be this one. Okay, so that's all. So let me say again, if that was a differential equation, how do we, first of all, step 1 will be get the equilibrium solutions. What does this mean? Look at this equation, 2y minus 3y squared, and set the right-hand side of this equation to 0. Okay, so this is the same as y times, and this is 2 minus 3y equals 0. So one equilibrium solution is the obvious one, y equals 0, and the other one is 2 equals 3y. So in other words, 2/3 equals y. Okay, so I have two equilibrium solutions. One is 2/3, so that's the constant 2/3 function. That's the function 2/3. And the other equilibrium solution is 0. That's the constant function 0. That's the constant function 0. Okay, now sketch the graph of this function 2y minus 3y squared. This is simple. The function looks like this. It's essentially parabola. It's a polynomial degree 2. 1, 0 of this polynomial is at 0, and that's the blue solution. The blue solution corresponds to this constant function 0. This constant function 0. And then the other solution, the red solution, this one, corresponds to this constant function 2/3. Corresponds to this constant function 2/3. I can sketch this graph. Okay, I have those two are the two equilibrium solutions to this differential equation. Now, what's happening between 0 and 2/3? Derivative is positive, but when the derivative is positive, then the function has to be increasing. So when you start at anything between 2/3, the function has to be increasing, but I cannot touch. So I'll have to approach the equilibrium solutions asymptotically. Will be asymptotically close to that one. If you start with another solution, it'll have to look like this. It will have to look like this, and so on and so forth. When you take any point that's bigger than 2/3, for example, this point, maybe 1, then you will see that the function is decreasing because the derivative is negative. And when you take any point that's a little bit less than 0, for example, -0 point, this point, the function will be decreasing. Okay, that's all what I have to say about stability, the phase plot, autonomous differential equations, and equilibrium solutions.